So what we will do today, right? We will go through the foundation of generative AI, right? It's a different kind of AI in the sense it is not about differentiating between cat and a dog, right? Or predicting a stock prices. It's a different kind of AI where we model AI to generate something new that it has not seen, right? So that kind of AI itself is a true intelligence, right? So this is where we will deep dive into the foundation of it, how we model something that can generate something totally new that has not been learned so far. Before that introduction, myself, Puru Chaudhary, founder of BrahmGAN. It's a 3D AI-based company. It pioneer in 3D AI development and blockchain development. So I will show you, what we can achieve it through generative AI. Many of you must have heard about ChatGPT, right? It is making a lot of noise nowadays. Many of you must have tried your hands also with ChatGPT. Some of you might have gone through Midjourney, right? Some of you might have gone through Stable Diffusion, Stability AI, and others tools that are available, right? So in our 3 sessions that we will have, we will not talk about any LLM, basically large language model, or any chat GPT stuff, right? Because there are many who are talking about it. But we will talk about the foundation of it. And if possible, if I see more people with a programming background in a subsequent session, we will have some hands-on also, but that depends on what kind of audience that we have today. So before that, right, I will directly show what generative AI is capable of through one of our product that we have built at BrahmGAN. So it is apps.bramgan.com. Currently, we are planning to build 3 pipelines. One is video to 3D, another is image to 3D, and next is text to 3D, right? As the name suggests, in first one we take video of an object, right? Say video of your own person, video of a person, right? We will be able to generate a 3D scene or 3D person out of it through that pipeline, right? That is our video to 3D pipeline. Currently, it is live, and if it is alpha version. The next 2 pipeline that we are building is image to 3D. We don't even require video now. If you give us a symmetrical image, we can always convert it into 3D. That's our second pipeline in research. And third is text to 3D, like Midjourney, right? You go and put anything you want to draw, right, on text prompt. Similarly, you can write it on text prompt, but the output will be 3D, right? Not like 2D that your Midjourney or Stable Diffusion or Stability AI is generating, right? So these are the 3 pipelines. I will walk you through the first pipeline that basically use generative AI with NERF as a tech stack. How many of you have known NERF? One of the video that we have taken of a small toy character, right? And this is how this video looks like. Okay, it is a common mobile phone that we have used to take the video and able to construct a 3D output or 3D asset out of it, right? And I will tell you the value that generative AI is adding to this. This was the video, and I will not go through each step of the platform. I will directly go to the viewer platform where you can see the output that we are able to generate out of that toy character, right? So it will take few seconds to download the model. Okay, now it has been downloaded. So if you see, we are able to generate the 3D model out of it, right? Just to tell you how much time it would have taken when someone would have built it the trivial way or the legacy way, it would have taken a week for 3 or 4 modelers to come up with a model only, right? it would have taken few days to come up with a texture, and then few more days to basically rig it or animate it. So out of out, it is hundreds of hour person work that would have gone into this. But AI, the generative AI, is able to within minutes, I will say, right? Currently, for a small GPU machine, it is taking us 10 to 15 minutes. But if we give a better system, it can be come down to a couple of minutes also, right? So this is the power of AI. Now you can think of at what scale we can develop game, right? Or say if Amazon you go, right, you see the 2D photos. If you can see the 3D photos, 3D scene of the object itself, right, 3D asset itself, then it will be a boom for e-commerce, right? It will be great for the e-commerce. Similarly, the VFX. Currently, if you see, you have seen VFX through that green background, right? They basically draw on green background. But with this thing available, you can draw the complete city, right? Mumbai city with the help of video, and then the city will be available to you, right? It will take lot of compute power and lot of money, but the time, right, to basically generate those things will come down very low. Okay, so first thing, right? I told you, I mean, what generative AI is capable of. ChatGPT is already doing disruption. Midjourney is also doing disruption. It is basically complementing the artist, right? Previously, if you see, artists used to put so much time into one thing. Now they are able to generate thing and able to build on that, right? So it's very complementary in nature. And what I have shown video to 3D is another aspect or another dimension that we are touching, where we can generate 3D output, 3D asset, or even metaverse from a video like nothing, right? So it's important to understand how generative AI works. So this session is all about generative AI. If you see here, right, before we say what is generative AI, we need to understand what is discriminative AI, right? So far, what we have seen, say pre 2014, especially, we are able to discriminate between what is dog or what is cat, right? We are able to discriminate which painting has been painted by a painter A or painter B, right? So it's very discriminative in nature, but it is not able to generate anything out of its own learning, right? So this is where the difference comes between what is generative and what is not generative, right? So what is not generative basically falls under discriminative modeling category, and all those who are coming from Kaggle background or other Hugging Face background, right? Mostly you have gone through discriminative modeling only. You have not gone through generative modeling. So generative modeling is basically it's a branch of machine learning that involves training a model to produce new data that is similar to given data set, right? So what it means is, if you see on the left side, if you have that data set available with you, and if you train that data set, right, and you are able to generate new asset out of it, new items out of it, right? If you see horse on the left and horse on the right, they are totally different, right? So some learning has gone through this, and by adding or sampling a different point in the dimension, right? I will come to the dimension later. You are able to generate something new, totally new, right? So if I tell you the difference between discriminative and generative in mathematical sense, it's a conditional boundary. Discriminative AI is basically a conditional boundary that you get between two classes of the object, right? Between a horse or a zebra, right? Between a dog or a cat. But if you are able to learn the underlying distribution or underlying joint probability, it means that you are able to generate it, right? So here, if you see, if it is a class of a zebra and this is a class of a horse, right? You are able to see the distribution. So even if a new point, if you take in this distribution, you know this new point will be zebra. Similarly, if you take a new point in this distribution, that new item will be horse, right? So where we have gone in last 10 years, right? 2014 is when Godfellow put his paper on GAN, generative AI. Before that, there was some work on autoencoders and others, right? With the help of that, we are able to generate few things. But the real breakthrough came in 2014 when we started generating human faces, right? So this is the journey that you see. 2014, we are able to generate a grayscale, very low resolution face. Then we moved to RGB in 2015. We are able to add more features like beard, hair, and other things in 16. 17 was another major breakthrough where we are able to create a super resolution human face, right? Then 18 able to capture wrinkles and others. 19, 20, 21, 22, 23. You can see, right, how well we have gone in generative AI. In just last 10 years, we are able to generate something that is not real, but it looks more real than the real thing itself. Okay. So I will come to I will tell about generative modeling in a simple dimension. It's a two-dimensional thing. I will take example of two dimension and try to explain it. But think of this not at two-dimensional, but as a multi-dimensional thing. But for simplicity, I will go via two-dimension, right? So I will give you one challenge. This challenge is if I say you have to you have to create a model that will create the distribution of it, right? I have given you these points on a two-dimensional map, and I say, why don't you give me a model that accurately define these points, right? So one of the simplest way is you will say, I can create a model, a rectangular model that covers length and breadth of these points, right? Right. So this is second part. That is the very simplistic model, right? You are able to give me a very simplistic model that say if my model is a rectangular model, it will cover all the points, right? Let's see few failures. Actually, these points are your map of your world, right? So if I draw the map of the world and I will say take a point in Alaska, the point B, it is outside your rectangle, right? It lies here. So your distribution is not correct. Similarly, if I say point A, which is part of the ocean, right? If I go by your distribution, you will say point A should be part of the data set, the original data set, right? But your distribution is not correct. You are not able to model your data set not correct. That's why you are getting a point in your current distribution or estimated distribution that is outside the model, right? Then there is a point C. Point C lies here because this lies here. It is part of your estimated model, right? So basically, what you have to do in generative AI is you have to model your distribution in a way that it covers your existing data set. Okay, you tried with a rectangle. It's a very bad example, but if you train enough, right, on enough data set, you will reach a distribution that is closer to the globe, right, closer to the map of the world. Okay, so that is the challenge of generative AI. If you know how to model your distribution closer to the data set that is presented, then you are able to generate it, right? So if I say take point B right here, if you have generated this A, B, and C, you could have easily created a point that lies within the world map, right? Or you could have gone to Australia or Africa or Europe, right? You would have created the right distribution around it. So the challenge of generative AI is learning distribution, right? So if I take back you couple of slides, discriminative AI only tells you what is A, what is B, or what will be the price of a stock at a given point of time, right? It can predict that. But generative AI, you need to learn the distribution, complete distribution itself. if you are able to learn the distribution, you can always sample it from the distribution and it will generate things for you, right? And this is where you will learn about it very soon. Before you go into our first generative model, I will take you to one more aspect of generative AI is representational learning, right? If you try to learn this distribution, right, what you will do is you will end up learning each point across the globe, correct? It's not easy, right? Learning so many high dimensional aspect is not easy, right? So what generally most of the GAN or most of the generative AI does is it learns the features or lower dimensional latent space, right? So if I tell you, if I give you a cylinder, right, and say how you will encode it so that I can generate any cylinder, right? Mathematically, how you can uh, decimate it so that you can generate any cylinder out of it, right? So if you see the properties or features of a cylinder, if I create a cylinder, right? So rather than representing or learning the complete cylinder pixel by pixel, what I will learn is I will encode this into a 2D space, right? A 2D space of length and radius, right? Or height or a radius. So I can pick any height, any radius, and I can draw or I can map a cylinder out of it, right? So in this case, this is a new data point, right? So this is my latent space where I have trained on these data, this data, this data, this data, this data, this data, right? But if I say I am giving you a length of 1 and radius of half, right? Can you draw me a cylinder? The answer is yes, because I know in two-dimensional space, length 1, radius 1 is this. Length 2, radius 1 is this point, right? I can easily decode it into something very, very new, right? This cylinder was not even present. So this is the latent space. Rather than learning everything in high dimension, most of the computer vision techniques learn it into features and then convert it into latent space and then convert it into or decode it into the real object, right? So this is a very important aspect, and you will hear this term latent space a lot. Any book you pick, you will hear this term latent space, embeddings, right? And you have to apply this principle everywhere, right? Any generative AI you will pick, there will be higher dimensional space and there will be lower dimensional space, right? And best way to learn is have this analogy with you, and anytime you come across these words, you can easily correlate what latent space means, what embedding means, right? Second, so this is the first part where we have gone through how generative modeling take place, right? So quick walkthrough again. So generative modeling is about learning distribution, right? Then it's about learning distribution accurate enough so that we can model the right world or the real world for us, right? Once we have modeled the real world, we can pick any sample, right? We don't have to choose this point, this point. I can choose any point in the sample and create a new output out of that, right? And this we already covered about latent space and embeddings. Second piece is the deep learning itself. This we will not touch. Next session, if we go for a hands-on, right? Then we will touch the coding piece of it, but theoretical piece, I am not touching deep learning, right? This is not, this session is not about deep learning, but learn about neural networks. Take any book. I personally like this book from Manning, Deep Learning with PyTorch. This book has been created by the author of PyTorch library itself. It's a very good book. Out of many books that you see online, I found this book really thorough in what they are selling, right? So I'm not promoting this book. I have nothing to do with the authors, but those who wants to learn deep learning, especially with the PyTorch framework, then you can buy this book or get this book can read from it. In subsequent session, we will learn about different methods that we have for generative AI, right? It is categorized into 6 different categories. One is variational and auto encoders that we will cover today. Second is generative adversarial network that we will cover in the next session. There are few more, but not popular, like autoregressive models. I know Google is using autoregressive model a lot. Then normalizing flow models, energy-based models. These are also the method to generate for the generative AI, but we will not cover those because they have become either obsolete or they are not in news anymore, right? And last is diffusion model and control net that we will cover in the last session. Okay, so before I go to variational auto encoder, I can take few questions. Any question, guys? You can write it on. I will give you a couple of minutes. You can write it on a chat. Nerf, Kumar is asking, Nerf, what is the use of it? So Nerf, Kumar, is a neural radiance field, right? It is basically for view synthesis. Okay, what it means is if I have to generate or create a 3D view in a 3-dimensional space, right? I will use this neural radiance field to generate it. Basically, you pass a ray through the camera, right, and try to sample the RGB value and intensity value across that camera line, right? And once you get that average value, then you assign that average RGB and density value in a 3-dimensional space, right? In that 3-dimensional space, if you cover all the points, that then you get your view, right? In this case, we have seen it, right? If I show you this, this is actually the model. I will show you the view synthesis also. Just give me a second. Actually, I said. So what you see there, right? There was what you see there was a 3D model, actual model that go into Unity or Unreal. What you see here, right? It basically the nerf applied to that video, and we are able to synthesize the view, right? It is not the video of an object. It's not a 2D video. We have taken a video of actual nerf, right? You are able to synthesize each and every point of that object and show it and capture it as a video, right? So nerf is a technique to basically synthesize view in a 3D space. Okay. Any other question, guys? So I will wait for a minute and then we will move to the variational auto encoders. Yeah, Alka, if you have any question, you can write it on text. Sorry, write it on chat box. So Alka, I think you want to say something. Avani, is it possible to mute participant, or I can do it?
Yes, Alka, I can speak now.
Good evening, sir. So actually, I'm unable to access my chat section. That's why I didn't able to write it. So actually, I wanted to ask that a map example in which you told about the difference of discriminative and generative. The Google Maps which we are using, they are not using they are still using deep learning models, right?
They are not using deep learning model as of today, right? So what they do is they take satellite video, they take drone videos, and then they try to map the Earth completely, right? But now they are using it. I am forgetting the name. not Google Street, but this year in Google I/O keynote, right? They have released a thing where you can have a 3D view of a city, right? Currently, you basically navigate in the 2D roads, right? But now you can actually move from one road to another road and another road to another place. So they are, for that they are using AI. But as of now, Google Earth and Google Maps both are Web2 based. Sorry, both are non-AI based.
So can you just explain me again that example for the generative part, how we are inculcating generative AI there? Because I'm not
Okay.
able to understand how the model is working.
Okay, I will. So in next section that I will cover. Right.
Okay, sir.
That VAE part, right? So it's a repetition, but it's a repetition in a context of variational auto encoder. So once we touch upon that, I think it will give more clarity how actually you are able to do the generative modeling. Okay.
Okay, sir. Thank you.
No worries. So I see one more question. Are dimension only for length and width? Answer is no, Kumar. Just for simplicity, I have taken 2 dimensions. But it can be multiple dimension, right? It is way complex mathematics that is going under the hood. Okay. I will share my screen again. Okay. So what is happening here, right? We learned about encoding, we learned about decoding, and I just throw up one term called latent space, correct? So in this case, what you are doing, right, or what you have done, you have taken an object, right? In that case, a cylinder. Remember that example of cylinder only. You define that cylinder in 2 parameters only. One is height, another is radius, right? So you are able to create a latent space of all the cylinder that is possible. If you can have height of 0 to infinity and radius of 0 to infinity, you almost cover every possible cylinder that can be made out of this universe, basically, correct? So what you have done is you have encoded cylinder into a latent space or 2D latent space of height and radius, right? In this latent space, if I say draw me a new cylinder, how you will achieve that? Assume that in the training data set you have 100 cylinders, right? But I said with the possible values of height 0 to infinity and radius 0 to infinity, you can have infinite number of cylinders, right? How? By learning only 100 cylinders, right? You are able to learn about infinite. You are able to generate infinite cylinders, right? Infinite possible cylinders. So this is that latent space, right? Latent space is basically your learning in low dimensional. Low dimensional in this case is the height and radius. And you know your height can move from say 0 to infinity and radius can move from 0 to infinity. You can select anything, right? You can select say 500 height and 500 radius, right? Decoder knows how to decode a 500 height and 500 radius cylinder, right? It knows how to make a 1000 meter base and 500 meter height length, right? So this is what encoding and decoding is all about, and it comes under auto encoders, right? So we will come to variational auto encoders later, but I hope you guys have learned about encoding and decoding. Alka, you had that question, right? I hope this answered your question.
Yes, sir.
Okay. Similarly, I will give you one more challenge. Assume you have say 10 kind of a clothes you have at your home, right? From jeans, from top, from shirt, right? From briefs to different from shoes to pajamas to so many things, right? If I give you a wardrobe, right, and say assign this or place this in wardrobe, right? how you will place it. You will place possibly all the or to start with, right? Not even jump there. You will try to place everything in one item in a one wardrobe. Okay, but you will not realize that if you have to pick a point, say jeans pant, right? And if you have not cluttered it in a single place, then you have to look at the wardrobe, right? And if your wardrobe has, say, thousands and thousands of clothes, then it will be very difficult to locate a jeans pant that you want, right? So this is a punishment for you, right? So punishment is what? You are able to put everything in the wardrobe, but you have not collate everything properly. You have not clustered jeans pant in one place, a shoes in another place, right? And try to create a distribution that is basically similar to your wardrobe now, right? One thing at a place, then you will see the distribution like this, right? So what it means is, if I show you this here, right? Assume that you have 10 type of clothes like t-shirt, trouser, pullover, dress, coat, and all those things. And if I do a color distribution out of it, this is how the color distribution will look like, right? Your model will learn something. That learning is nothing but creating a distribution, right? Creating that mathematical equation or probabilistic distribution, which basically say this distribution belongs to this. There are certainly some errors, right? AI is not error free. If you see, there are some greens and violet between this orange and red, right? What it means is it is not error free, right? Nothing is error free. Your generative AI will also make error, and you have to ensure that your distribution is close enough so that your error becomes less and less, right? In the example of the wardrobe that I have given, if I say, if you keep your say trousers, right, at different places in the wardrobe, then your distribution is not correct. But if you try to keep, say, out of 10 trousers, 9 at one place, 1 at other place, then your error probability is 10%, right? But if you keep all your trouser at one place, then your error is 0%, and you can easily track your clothes in the wardrobe. It's an infinite wardrobe, assume. So it's easy to get it. Okay. So this is a neural network. Neural network, as I told, we will cover in next session. We will cover the GAN, generative adversarial network, and we will try to do hands-on if I see audience coming from the coding background, right? So I will not touch upon it. I will come back on this on next time we will have generative AI session. Okay. Now you will ask me what is variational encoder in this case, right? There are still some issues. You are able to pick any sample in the distribution, right? But still this distribution is not correct. It has a few issues. Your distribution, if you see, right, it is not cluttered around the center, right? It is not so if you select this distribution, right, or this sample, right, your AI will not able to give anything. If I try to map this, it is able to map something like this, right? This is not a cloth, right? More you are closer to the truth or distribution, then you are able to draw a shoe or a trouser or a sandal or something like that, right? But if you repurpose this model or repurpose your distribution in a way where you can have a variation around it, right? That becomes your variational encoder. So if I give you this auto encoding, in this case, what you are doing, you are taking a cloth, putting into a two-dimensional sheet, right? But if you choose a sample near it, right, it will not give you the right kind of t-shirt, right? But if you create a different distribution out of it, right, that can give a different variation, that will give you more and more option of generating new content, right? That's why it becomes variational encoder. So in this case, it's one-on-one mapping. So if you see the original architecture, here you had encoder, simple linear mapping, and then you are decoding it, right? So it was easy, but it has its own problem. Like it was not able to generate new content easily. It is able to, if you sample anything, right, it can give you a lot of garbage also. This is where variational auto encoder comes into the picture. Variational auto encoder is basically a bell curve or a Gaussian distribution. Okay, for every point you will encode, it will encode it as a distribution, not as a simple point in two-dimensional space, right? So if you select any point in this distribution, it will be able to generate this t-shirt as close as possible as real, right? But if you see normal auto encoding, that was not the case. Okay. So if I see mathematically what it is, basically your Gaussian distribution is basically a function of your mean and variance. Variance is basically the square of your standard deviation, right? So these are mathematical terms. Those who are from statistics background, they can easily relate what Gaussian distribution is, what mean is, or what log variance is, right? Now, if you see right, the left side and the right side, if we sample it, right, if we take the sample on the right side, we are able to generate more distribution, right? We have more, say, t-shirts. We have 1, 2, 3, 4 t-shirts. In that, we have one t-shirts, right? We have multiple sandals and shoes, right? So we are able to generate more variety of stuff and more accurately stuff through variational encoder, right? So this is how it differs, the auto encoder and variational encoder, right? We will not go into the code of variational encoding. We will, if we have to code, right, we will do it for stable diffusion and GAN, which is basically generative adversarial network. So I will take a pause and take a question from your side. So for coding, I want to know how many of you are hands-on with some AI stuff or some machine learning stuff, right? If we need to have that session, there should be good presence, or at least people should be aware of coding. So either you can raise your hands. I see Alka, Kumar, you are aware about machine learning coding. Right, so I will discuss with Avani on how we can proceed with the next session. Right, so if coding is required, we will have the coding session. Otherwise, we will directly jump into the GAN session.
Sir, will it be possible for you to show me, to show us how the modeling part is using the variance and that mean that model will be working?
How variance come again?
You told that in this second technique of that auto encoding part, we used a layer of variance and mean.
Correct. So if you see this distribution, right? So in this slide, my left side is of normal distribution, right? It's a one-on-one mapping of object in two-dimensional space. Okay. And the distribution look like this. If you see the color of that distribution, it is like this. Okay. If you try to sample it from here, right, it may not be able to create an object out of it, right? Or if you say 50% distribution, right, you say the 50% of the object is of one kind only, right? There are two problems with it. Are we able to generate it accurately? And if I am able to generate it, I am able to generate it of different variety or not, right? But if I see the normal distribution, if you see this color wala distribution, the more red and orange you see, right, it is of only two types, right? Other 8 types belongs to other 50% of the distribution. So tomorrow, if I have to create an object, right, then I will get 5 times a same object, right? And another 5 times I will get a different object, but the probability of distinct object, right, will be less. So that has been captured in this slide, the last slide, result slide, where this is the original distribution, and this is your variance distribution, right? You are able to model it on a Z mean and Z variance. Okay, your encoding is on mean and variance, and this time it is more dense. It is more centered around the center, right? So in this case, if you see the output, right? If you try to sample this blue dots, you get a different output, right? You had only one T-shirt. In this case, you had 1, 2, 3 T-shirts, right? Or even 4 T-shirts. You have multiple sandals, multiple types of sandals. You have multiple jeans. You have bags, right? So through the help of variational encoding, you ensure that your distinctness of generated object is there, and you ensure the quality of the generated object is far better than what you get in one-on-one encoding. So in one-on-one encoding, you get a simple sandal, right? You won't get a different sandal, a new generated sandal, right? So this is the difference that you see between autoencoder and variational autoencoders.
Okay, sir. In theoretical sense, I got the meaning. Will you show us with the mathematical modeling part also?
Mathematical modeling in the sense
Coding part.
Coding will no. So coding I will take in next session when we do the GAN, right? There also we will cover this Gaussian model. Have you heard about Gaussian distribution by any chance in statistics?
Yeah, in stats, I have heard of it. Gaussian distribution, normalization, that all those curves. Bell distribution also.
So mathematically, this is this curve only, right? So your mean is the mean, basically you're averaging out everything and then taking the mean of it, right? Variance is about how it is concentrated towards the center.
Standard deviation, yeah.
Yeah, how it standard deviation is square root of variance, right?
Yeah,
so
how it is concentrated in the center, like curvature, axis के बीच में कितना mean normalization जैसे concept.
Correct. So same thing is happening here. Now our distribution is centered around center, right? So mathematically, what you see here is happening in our learn distribution also here, right? Previously it was everywhere. Now you are learning on a mean and variance, or say standard deviation, right? So it is centered closer around the center. It is more dense than what you see here. Right? But coding perspective, I doubt most of these libraries, right, are very high level libraries. There is a lot of abstraction going on. You don't have to write any of this mathematical model yourself, right? You use these libraries like PyTorch or Keras to write these models. So this will come out of the box.
I usually code with TensorFlow and Keras.
I will go with PyTorch, but if you guys are TensorFlow, if you guys are using TensorFlow or Keras, then we can change it also. I have some experience. I will change the slide where we can have Keras. Okay, I think we are good for today. Thank you guys. Thanks for joining. We'll meet again in next session.